Alrighty, good morning everybody. Welcome back to Calc 3. Plan for today is we're going to finish off Standard 10 by kind of talking about a special variant of the chain rule. As far as homework for Wednesday goes, on Wednesday we are going to have a quiz over Standard 10. I encourage you to try out some of the practice problems from the book that I posted on Blackboard for that. And as far as office hours go, got office hours this afternoon from 2 to 3. Tomorrow morning, 10 to 10:45. Tomorrow afternoon from 1 to 2. And Wednesday, the hour before class, and from 2 to 3. Any questions or comments before we get started for today? So Wednesday and Friday we'll do Standard 11, which will be about the directional derivative, how you take the derivative of a function in directions other than just towards the x-axis or towards the y-axis. And then after the break, as I said, that Wednesday after break is when we'll have our exam over 1 through 11. By the way, did y'all hear about the circle that was super well educated? I hear it has a whole 360 degrees. Okay, so just to do a quick recap from last time. Last class we talked about the Calc 3 version of the chain rule. Where we said that if g is a function from Rn to Rm, and if f is a function going from Rm to some Rp, then the composition, f composed with g, is going to be a function that goes from Rn to Rp, and it has formula equal to the derivative of f composed with g is going to be the derivative of f evaluated at g of x, is that some vector x where x is in Rn, where the derivative of f composed with g evaluated at x is the derivative of f evaluated at g of x multiplied by the derivative of g evaluated at x. Basically the same rule as the Calc 1 version of the chain rule. And in Calc 1, we said that the derivative with respect to x of f composed with g of x is f prime of g of x multiplied by g prime of x. The main difference here is that in Calc 1, f prime of g of x and g prime of x were just scalar value expressions. Whereas the derivative of, in the Calc 3 version, the derivative of f evaluated at g of x and the derivative of g were multivariable for multivariable functions, so those derivatives were matrices that we had to multiply together. But it came out to the same thing. And today, it came out to the same thing in the sense that for both ones, you're taking the derivative of g, or g prime of x, and you're multiplying by the derivative of f evaluated at g of x. And today, I want to look at a special example, a special case of the chain rule. Where, if you're in the packet, we're going to be starting on the page that says, in this case where f is a function from Rn to R at the top. So here, we're going to be looking at the case where f is going to be a function from Rn to R, and g is going to be a function that goes from R to Rn, where n could be anything. Which, if we draw the little picture here, it's going to look like this. G is going to take us from R to Rn, and f is going to take us from Rn to R. What would happen if we compose these two functions? This function g, f composed with g, where g starts in R and ends in Rn, and f starts in Rn and ends in R. What can we say about where the function f composed with g is going to start and end? Yeah,
Start and end. Rn.
It's going to start in Rn and end in Rn.
Oh, is it? Sorry, other way around. Let's start at R and then.
R. Yeah. If we were to do G composed with F, that would actually start and end in Rn. But F composed with G, where we do G first and then F, is actually going to be a function that starts in R and ends in R. And in fact, something interesting that's going to happen is that F composed with G is going to be a Calc 1 function, meaning it's going to be a function that takes in scalar values as its inputs, because we're starting over in this copy of R, and then if we do G and then F, our outputs are also going to be scalar valued expressions. So F composed of G is going to be a function like f of x equals 3x squared plus 6. Even though if you were to do G and then F, you have to do a pit stop at Rn in the middle. And so F composed of G might be a Calc 1 function, even though F and G themselves are not. F is going to be a function that takes in vectors as inputs. G is a function that's going to spit out vectors as outputs. But if we were to do G and then F to a single scalar, we're going to end up with a scalar. And so in that sense, F composed of T will still be a Calc 1 type function. So if we were to kind of write this out using, say, some general formulas, if we were to say, let's say F is a function that's going to take in some x1, x2, up to xn, and is going to spit out a scalar valued expression. Whereas if G is going to be a function that takes in a single variable, which I'm going to call t, because most of our examples today are going to use t parameters for time. It's going to spit out a vector with n components to it, some g1 of t, g2 of t, all the way up to g sub n of t. And if these are our two functions, the composition of the two would be f composed with g, evaluated at t, would be f of g of t, which is f of g1 of t, comma, g2 of t, up to gn of t, by definition. Well, if f is going to be a function that takes in n components and spits out some scalar expression, if the components that we're plugging into f are just the component functions of g, meaning g1 of t, g2 of t, up to g sub n of t, then when we take the composition here, f of that expression is just going to be some scalar expression in terms of t. And if we were to take the derivative of this expression, what we would end up getting, the derivative of f composed with g evaluated at t, it's going to have a formula of del f del x1 evaluated at g1 of t multiplied by d g1 dt plus del f del x2 evaluated at g2 of t multiplied by dg2 dt, etc., all the way up to del f del xn evaluated at g sub n of t multiplied by dgn dt. And this formula right here is going to be sort of our special case version of the multivariable chain rule. It's going to be the chain rule in the case where f is a function from Rn to R and g is a function from R to Rn. In terms of n? Or not in terms of n, in terms of t? Sure. Something like f composed with g of t is going to be t squared minus 5. It's a scalar expression in terms of t in that there's only one component here, the single expression t squared minus 5, and in terms of t just means t is the only variable shown. So if, for instance, we were to have something like g of t equals, I don't know, t comma t cubed, and f of x comma y is x squared y minus 2x. If we were to take the composition of these two functions, both of which are sort of Calc 3 functions, the composition needs more space. I'm going to erase this. The composition of those two functions would actually just be a Calc 1 function. And if you were to take f of g of t, you would get f of t comma t cubed, which would be, let's see, we're plugging in t for x and t cubed for y. So we get t squared times t cubed minus 2x, so minus 2t. And we just end up with this sort of Calc 1 function where we take in an input t and spit out something like t cubed minus, or t to the 5th minus 2t. In theory, this is a function you could have graphed in a Calc 1 class, whereas f and g, both individually, are not functions you knew how to graph in Calc 1. Does that make a bit more sense? Sure. So this is going to be what our derivative of f composed with g evaluated at t looks like. It comes from summing together a bunch of expressions of the form del f del some variable x I times the derivative of the ith component function of g with respect to t. If we were to make a little diagram for kind of what the multivariable chain rule in this case ends up looking like, it sort of ends up looking like this, where we're going to start with a single variable t. The function g is going to map t to n different component functions. Some g1 of t, some g2 of t, etc., down to some gn of t. And so the function g is going to work by taking in t and spitting out these n different component functions, g1 of t, g2 of t, down to g sub n of t. And then the way the function f works is it's going to take all of these different expressions, the g1, the g2, and the gn, and it's going to spit out some scalar expression in terms of t. So that g by itself will take in a single variable t and spit out a lot of different component functions, g1, g2, up to gn. F is going to take each one of these n components and somehow combine them all to get a single scalar expression, so that the composition is just taking in a single variable t and spitting out just some scalar expression in terms of t, like t to the 5th minus 2t, even though as part of the process in the middle, g is going to take the original t to several different component functions in the middle. So here, for instance, we would say that our g1 of t was t, our g2 of t was t cubed, and so we started by sending t to a copy of t and t cubed, and then f kind of combined those two expressions in a way to give us back our single scalar expression in terms of t, t to the 5th minus 2t in this example that we were looking at. And according to this formula, the way that we would differentiate the composition of doing g first and then doing f is we would sort of travel along the different arrows. So this first expression, del f del x1, evaluated at g1 times dg1 dt, what that's telling us is take the derivative of the function f that combines all of these different functions, differentiate along this arrow, meaning with respect to x1 of g1 of t, multiply by the derivative going down this arrow from t to g1 of t, which is just going to be dg1 dt. So essentially, we're taking a derivative here of multiply the derivative of this arrow times the derivative of this arrow, We're then going to add what you get if you multiply the derivative along this arrow by the derivative along that arrow, and et cetera, et cetera. We're in the last step. We're going to take the derivative along this arrow, differentiate f with respect to the last component function of f, and multiply by the derivative along this bottom left arrow, the derivative of g sub n of t with respect to t. And the reason why I'm drawing these kind of complicated diagrams and giving these sort of scary-looking formulas is because we're going to be using the chain rule in just a second here to solve some word problems. To be able to actually go through and look at some scenario where a stick of butter is melting or a plane is spiraling out of control, and looking at what sorts of things can we say using this sort of chain rule composition formula. But before we go on to start looking at some examples of where we put this into practice, what questions do y'all have so far? Because I've kind of talked for a long time here and I've thrown a lot at you. I want to see what questions you have before we go on to start applying this with an example. Yeah. Correct. So here, this is our g1 of t, this is our g2 of t. Where g1 and g2 themselves are going to be calc 1 functions, functions that take in t, spit out some scalar expression in terms of t, like g1 of t equals t, g2 of t equals t cubed in this case. Let's do an example. So I'm going to be on the next page in the packet for, starts with, suppose a rectangular stick of butter. So here's the problem. We got a rectangular stick of butter that's melting. Here's a picture of what our stick of butter is going to look like. I'm going to label these two sides S and this side L. So we kind of have a square base in a rectangular fashion. So a stick of butter is melting. And what we know about the stick of butter that's melting is when L is equal to 6 inches and S is equal to 1.5 inches, L is going to be decreasing at a rate of 0.25 inches per minute, and S is going to be decreasing at a rate of 0.125 inches per minute. So we have S and L. Our stick of butter is in the microwave. It's melting away. It's shrinking. And we know when L is 6 inches and S is 1.5 inches, L is going to be decreasing at this rate. S is going to be decreasing at that rate. So we know how fast S and L are shrinking at that point in time. And the question I want to ask is, at this point in time, how fast is the butter melting overall? So in other words, at what rate is this solid chunk of butter going to be melting away? So this is an interesting problem in that we're not actually given any formulas to work with. What we're given is that we know at some point in time when L equals 6 and S equals 1.5, we know the rates at which L and S are going to be decreasing. So first of all, let's ask the question, let's ask, what is this question looking for? We're looking for, at at what rate is the butter melting overall? We have this solid sort of volume thing of butter, and we want to ask, how fast is it melting? What expression can we find that would tell us sort of how fast is this volume of butter going to be melting away? Well, it's probably going to be the derivative of something. But the derivative, what could it be the derivative of? If we wanted to talk about the stick of butter as a whole. If we're thinking about like its volume melting away. Or? We could find del S del T, potentially. Problem is, that just tells us how one single aspect of the piece of butter is going to be shrinking. Just kind of this cross-sectional edge. I'd like to have something that's going to tell us about the stick of butter as a whole. Okay?
Well, the volume of the stick of butter is S squared L, so find the derivative of that.
Ah, the derivative of volume with respect to time. Yeah, we could certainly do that. So the question I think we really want to ask, what is the derivative of volume with respect to time? Where V is going to be the volume of the stick of butter. And Sarah, what did you say? What did you say? I think you gave a formula for what you think V is.
S squared L.
Yep, those two are S. I like it. You have a kind of a rectangular prism here. The volume is going to be length times width times height. In this case, height and width are going to be the same. They're going to be S. And the length is going to be L. So I think we can use that formula that the volume is going to be equal to S squared times L. Kind of this cross-sectional side S squared to give us width times height, and then multiplied by L to multiply by the length of this rectangular thing. Cool. So we know what the volume is in terms of side length of S and L. So Sarah, if we wanted to differentiate this with respect to t, with respect to time, to tell us how is the volume changing over time, what would we get?
We get
I think we would get a bit of a mess. Yeah. It's not just going to be so simple as to say differentiate that with respect to t, because I don't see any t showing up in that expression. At least not the way it's currently written. We could write it in this form to say that as time is changing, as time moves on, S, L, and V are all going to be changing. Meaning, as the stick of butter melts, S is going to be getting smaller, L is going to be getting smaller, and V is going to be getting smaller. So another way we could write this is to say that the volume is equal to S of t, quantity squared, times the length, all of which are going to be functions in terms of t here. Because as t changes, S is going to change, L is going to change, and V is going to change. If you look at the stick of butter 5 seconds versus 5 minutes after we put it in the microwave, all of these values, S, L, and V, are probably going to be different from each other as the stick of butter slowly melts away. So something that we're going to need to do is to figure out how can we differentiate volume with respect to time here. And what I think is going to happen is we're going to get sort of a diagram like this one I'm currently erasing, where we're going to start off with a time parameter t. We can find what S of t and what L of t potentially are. And then S and L themselves, which are functions of time, volume is going to be a function in terms of those two variables. Meaning volume is a function of S and L. S and L themselves are going to be functions of the same variable t. And so we're going to end up being able to use sort of this multivariable version of the chain rule to differentiate volume with respect to time by kind of working our way down through the middle and differentiating volume with respect to S and L kind of along the way. So one thing I think that's helpful to do before you dive too deep into sort of a problem like this is to ask the question of what do we actually know? Well, we know that at some point in time, some fixed point in time, we're never given a specific value for it. So I'm just going to say at some t equals t naught, we know that the length is going to be 6 inches at that point, and that s is going to be 1.5 inches. We're not told when that t naught is. We're not told, for instance, is it 2 minutes after putting the butter into the microwave? Is it 10 minutes? Is it 0.6 minutes? We don't know when it is, but at some point in time, after we put the stick of butter into the microwave, we know that at that time t naught, the length is 6 inches, and s is going to be 1.5 inches. How can we encode this piece of information in sort of a formula regarding something related to t naught? This fact that L is, at this point in time, L is decreasing at a rate of 0.25 inches per minute. How can we write that down as a formula? The fact that at time t equals t naught, L is going to be decreasing at a rate of 0.25 inches per minute. Emily? With respect to? I like it. Yeah, we could say, oh, that came out high pitched. Sound like a dog. We could say that dl dt evaluated at t naught is going to be, it's going to come out to what, Emily? Why negative? Yeah, since L is going down at a rate of 0.25 inches per minute, we know dl dt evaluated at t naught is going to be negative 0.25 inches per minute. We could say something about the derivative of L with respect to time at that point in time, which is that dl dt came out to negative 0.25. How can we say something similar and write down this last kind of bit of information using a sort of formula like we did? Whit, do you have any ideas on how we could take the fact that S is decreasing at a rate of 0.125 inches per minute and sort of write it out?
Yeah, ds dt is equal to
ds dt at t naught is going to be equal to, what did you say?
negative 0.125.
Negative 0.125 inches per minute. Yep. Negative again because we said that S is decreasing at that rate rather than increasing. So here's kind of the pieces of information that we're given. We know that we have some point t naught in time, and at that point in time, we know the values of L and S, that L is going to be 6 inches, S is going to be 1.5 inches. If we take the derivative of L and S with respect to time at t naught, we know that dl dt at that point is negative 0.25 inches per minute. ds dt at that point in time is going to be negative 0.125 inches per minute. Do we know if dl dt and ds dt are always going to be negative 0.25 and negative 0.125? Meaning, does it say anywhere in the problem we know that S and L are going to be decreasing at a constant rate? No?
No, because it just says at t naught, this is the rate.
Yeah, we just know that that's the values of dl dt and ds dt at that single point. So at the point when L equals 6 and S equals 1.5. Because it could be that the rate that dl dt and ds dt are going to be changing over time. Maybe we put the stick of butter in the microwave. We're like, nah, this is going too slow. Let's nuke it faster. And then we turn up the temperature or something, or turn up the radiation, step away from the microwave. Don't play around with radiation, kids. But it could be the case that dl dt and ds dt are not the same, always going to be the same. So we can't say dl dt is always negative 0.25. We just know that it's that value at our unknown t naught. And ditto with ds dt. So our goal is going to be to somehow use these pieces of information to tell us what's going to be dv dt at t naught. At the point in time, t naught, when s is equal to 1.5 inches and L is equal to 6 inches. So let's see what happens if we play with this formula here. Because we know dv dt is the derivative of volume with respect to time. One way we can think about doing this is if we let g be the function that takes in time and spits out s of t and L of t, and if we let f be the function that takes in s of t and L of t and spits out the volume, v, with respect to s and L, I think we should be able to use kind of this multivariable chain rule formula to help us find the derivative of volume with respect to t. Because you can sort of think about the composition of these two functions, f composed with g at t to be the volume at any given point in time. Because g is going to take in t and spit out s of t and L of t. F is going to take in these two values, s and L, and is going to spit out the volume corresponding to what s and L are equal to. And so if we write that out, we can get that g of t is going to be equal to s of t comma L of t. F of t, which is just what we're calling volume, or not f of t, f of s comma L is what we're calling volume, meaning if we were to take in volume s and L, our function f here is going to be spitting out what's the volume for that given value of s and that given value of L. And I think we should be able to find explicit formulas, or an explicit formula, I should say, for one of these two functions. The function that tells you at any value of t, what's s of t and L of t going to be equal to, or the function that takes in a value of s and a value of L and tells you for that s and that L, here's what the volume is. Which one of these two functions, f or g, do you think we should be able to find an explicit formula for? There? So we should be able to say at any given value of t, here's exactly what s of t is and here's exactly what L of t is.
You can definitely say it for t naught.
We can certainly say that at t naught, but can we make statements about values of t in general?
I don't think so.
I was gonna say, I don't think we can. I don't think this information allows us to say what's L of t and s of t going to be at any point. We just know what those are at this one value of t naught. So what about our f here? Do we have an explicit formula that's going to tell us, given what s and L are, here's what the volume is? I'll give you a hint. I see it written on the board somewhere. Well,
So it should just be the s squared times L.
yeah. I think, Sarah, that's actually the formula you said earlier. Is exactly what our f is going to be. It's going to take in an s and an L, and it's going to spit out the volume according to that, which is just going to be s squared times L. And now, I think we finally have enough information that we're going to be able to use this derivative formula. That the derivative of f composed with g Because f composed with g is going to take in a time, and it's going to spit out the volume at that time. We can use what we know about S and L as sort of our midpoint step along the way to now tell us what exactly the derivative of volume with respect to time is going to be. Yeah, I think we can erase this now. So let's see what we would get. So at t naught, the derivative with respect to t is going to be the same as the derivative of f composed with g with respect to time at t naught. According to the chain rule formula we have on the right-hand side of the board, f is a function in terms of s and L. We should be able to write this as the derivative of f with respect to s, del f del s, evaluated at s of t naught, times the derivative of s with respect to time at t naught, plus the partial derivative of f with respect to L at L of t naught. Or not at L of t naught, but just at at t naught, I should say, multiplied by dl dt, evaluated at t naught. So in using this multivariable version of the chain rule, what we're really doing is we're multiplying partial derivative of v with respect to s times derivative of s with respect to t, adding that to partial derivative of v with respect to L times derivative of L with respect to t. We're sort of multiplying things across the same sort of path of arrows. Derivative of volume with respect to s times s derivative of s with respect to t, derivative of v with respect to L times derivative of L with respect to t. That's what our multivariable chain rule here is telling us we need to be doing. So, any questions so far? Yeah, Emily?
Okay, so when you're trying to not formula this problem, you know, not so I understand how S is x1.
Yeah, so here we have like x1 equals s, x2 is equal to.
Right. So then I don't understand how like G1 is also.
What's happening to G1? Technically, this is saying at the point s of t naught, meaning at the point when we're plugging in t naught into the function s. But in this case, that's the same as just saying at the time t naught, because at the time we're plugging t naught into s, it's going to be the same as just the time t naught.
And then
I'm trying to do this with as few variables as possible, so to speak.
yeah. Okay.
Sure. So let's start plugging in things. We know what ds dt is at t naught. We know what dl dt at t naught is. What's del f del s going to be? That's something we don't know yet. Meaning, if we know that f of s comma L is equal to s squared times L, which one are we doing first? What's del f del s going to be? We differentiate s squared times L with respect to the variable s. Yeah?
2LS.
Yeah. Derivative of s squared times constant is just going to be 2s times that constant. So I'm just going to say 2 times s times L. And the derivative of f with respect to L, we're differentiating s squared times L with respect to L. That one, what are we going to get?
S squared.
Just derivative of constant times L is just going to be that constant, in this case, s squared. So if we plug that in here, when we take dv dt of t naught, our del f del s at t naught is going to be 2 times S of T naught times L of T naught. And then we'll still have our ds dt evaluated at T naught, plus del F del L, which is just going to be S squared, so S of T naught squared, times ds dt evaluated at T naught. So here, I'm just taking our expressions for del F del S and del F del L and kind of plugging them in here, where del F del S at T naught is the same as taking 2 times S times L, where S and L are both being evaluated at the point T naught in time. And now I think we can start plugging in some numbers. We know what S of T naught is. That's just 1.5. So this will give us 2 times 1.5 times L of T naught, which is 6, times our ds dt, which is the negative 0.125 inches per minute. So now, all the stuff we found at the start of the problem, we can just plug in those numbers now for L and S and dl dt and ds dt at T naught. Plus, what are we going to get if we were to plug in S of T naught squared times ds dt? What numbers are we going to plug in here then? Katie, any ideas?
So right now I'm stuck on why both expressions are dotted with dsdt.
That's just coming from this formula over here. Like the del F del S times ds dt, that's just coming from the del F del x1 times dg1 dt. The g1 here, you could think of as being just S of t, and the g2 of t, you could think of as just being the L of t. So here the ds dt evaluated at T naught is just coming from our dg1 dt expression, the derivative of g1 with respect to t, or the derivative of s with respect to t. Oh! Right there, you mean? That's a typo. That should have said dl dt. That's okay. We'll number crunch here in a second. Right now we're just plugging numbers in. And what are we going to multiply our 1.5 squared by? I don't think we have a formula for L of t in general, but we do know the derivative of L at that point T naught with respect to t. Yep, times negative 0.25. Which when we number crunch, I already number crunched that so you don't have to, that's going to be about negative 2.81 when you evaluate this whole mess. Derivative of volume with respect to time at T naught, this unknown T naught value, is going to be negative 2.81. What's the last thing that we need to do with our answer in order to say, we're done with this problem, we have an answer for how fast is the volume going to be decreasing? Huh?
Give it units.
We need to give it units. This is a word problem. This is looking at how fast is the volume decreasing. We can't just say, oh, the volume is decreasing at a rate of 2.81. need 2.81 watts. And so something to think about is if we're looking at the derivative of volume with respect to time, we should probably have for our derivative units of volume divided by units of time. So what's going to be our units for volume divided by units of time here? Keeping in mind that S and L are both being measured in inches, and our time component is going to be minutes. Oh? Not inches squared per minute. Inches squared per minute would give us something like change in surface area per unit of time, but you're close. I think we're going to need inches cubed because volume's going to be measuring in inches cubed. There we go. About negative 2.81 inches cubed per minute. So this is a question on a quiz, by the way, or an exam. Since I don't let you use calculators, the numbers would be a lot nicer to deal with. I'm not going to make you multiply that out by hand because that doesn't sound fun. But the idea here of being able to differentiate volume with respect to time by kind of working our way and multiplying across each path is an important one in how the chain rule works. Essentially, what we're doing here, the formula we ended up using is the formula that the derivative of volume with respect to time is going to be del V del S times ds dt plus del V del L times dl dt. Sort of the formula we ended up using here, where volume is a function of S and L are themselves a function of t. To find the derivative of volume with respect to time, we need to take the partial derivative of volume with respect to S times the derivative of S with respect to t, and add that to the derivative of volume with respect to L times derivative of L with respect to t. And that's kind of the essence of how the multivariable chain rule is going to work. Is you just kind of multiply across each kind of path from t to the final expression, and you add across kind of each product you get going through each arrow. The product across kind of this top sequence of arrows plus what you get when you multiply along this arrow by that arrow. Question. What's different about the way I wrote these two expressions, other than the fact that one has v and one has t in it? There's a little bit of different notation being used here. Anybody point out what that was? Well?
The first one's using del.
Yeah, the first one's using del, and the second one's using d. Del v, del s, and ds dt. And Will, why did you say we're using a different notation here? Bingo. When we say del v, del s, what we're saying is the partial derivative of volume with respect to the variable s. Whereas when we're using this notation, ds dt, what we mean is just the full derivative of s with respect to t. The difference being v is a function of multiple variables. V is a function of both s and l. And so when we differentiate with respect to s, that's only a partial derivative, so it's giving us the derivative with respect to one of the two variables. And that's why we use the del symbol, is because this is a Calc 3 type derivative in that we're taking a partial derivative here. Whereas ds dt, that's a sort of derivative you saw in Calc 1, where s is only a function of the variable t. So we could have written here just s prime of t, if we had wanted to, for instance. Just a standard Calc 1, we have a function of one variable, we're differentiating with respect to that variable. And so that's why I'm using these sort of different notations of del's versus d's. Whenever you see del's, I want you to think about partial derivatives, whereas d's, ds dt, something like that, that just means the calc 1 derivative. You have a function of one variable, differentiate with respect to that one variable, as opposed to function of v with respect to multiple variables, differentiate, take the partial derivative with respect to only one of those multiple variables. So basically, our approach, and I encourage you to do this for future problems, is we started by writing out all the information that the problem gave us, which I think was helpful. Just the fact that like L of T naught, S of T naught, dL dt, ds dt at T naught, we knew what all those values were. We then kind of used this diagram to help us kind of write out how this chain rule is going to work by taking derivative of volume with respect to S times derivative of S with respect to T, derivative of V with respect to L times derivative of L with respect to T, add them together, and that gave us the derivative of volume with respect to T. Our volume here was sort of the composition of our f and g functions. It's very likely that on a quiz or a test question you'll get something like this where I'll just set up a scenario for you and it's up to you to kind of draw out your diagrams to sort of see what things you're going to need to be multiplying and adding in the correct order. Let's do another example. And for this one, is everyone, I should have asked first, everyone okay if I erase the line of equation? Yeah. Suppose a plane is going to fly along a curve x of t, comma y of t, comma z of t is going to be equal to 2 cosine of t, comma 2 sine of t, comma 3t. So basically, we have a plane that's flying through space in a path that looks sort of like this. Kind of corkscrewing straight up. By the way, if you're ever flying on such a plane, pray. Your plane should not be doing that unless you're a stunt pilot or something. Plane's flying along this curve, though, this parametric curve, and the pressure, the plane suddenly encounters a weather front. Gadzooks, so that the barometric pressure is varying a lot from point to point, meaning at each point in three-dimensional space, the air pressure is going to be different. And the air pressure, it turns out, is always going to be equal to P of xyz is 6x squared times z over y atmospheres. So if you know at what point you are in space, what point in three-dimensional space, this will tell you what's the air pressure at that point. And the question is, at t equals pi over 3 hours, how fast is the pressure changing? So this time, we're given a little bit different type information. We're given explicit formulas for everything, which makes it a little bit easier. We know that we're starting off that x, y, and z are all going to be functions of time. Basically, the x, y, and z coordinate of what point the plane is in the air is going to depend on time. We also know that air pressure, P, is going to be depending on the x, y, and z coordinates. And that wherever your x, y, and your z are, all of which are dependent on time, is going to tell you what the air pressure is going to be equal to at a given point. And so what we'd like to do is we're looking for how fast is the air pressure changing at time t equals pi over 3. In other words, we want to know what is the derivative of pressure with respect to time at t equals pi over 3 hours. So what do y'all think? How can we set up an expression that will allow us to differentiate pressure with respect to time? Well, I think we can use the multivariable chain rule here to help us kind of come up with an expression for what dp dt is going to be equal to. And that we should be able to kind of travel our way backwards across each path. And for instance, along our top path, we'll get that the partial derivative of p with respect to x times the derivative of x with respect to t. Jacob, what could we add if we wanted to differentiate across the middle path?
Oh, okay. Partial derivative of p with respect to y and derivative of y with respect to t.
Yep, like that. And how about Olivia? How about across this kind of bottom path?
Partial derivative of p with respect to z times the derivative of z with respect to t.
Like so? I like it. So ultimately, this is going to be the expression we need to find. Well, specifically, we need to find this at the time t equals pi over 3 hours. So let's see if we can do that. So the first thing we're going to need is we're going to need partial derivatives of p with respect to x, y, and z. So we put in some side work over here. We'll need del p del x, del p del y, and del p del z. If we differentiate p with respect to x, if p is equal to 6x squared times z over y, Lindsay, what are we going to get if we differentiate this with respect to x?
It would be 12 z x over y.
Derivative of 6x squared is just 12x with respect to x. Multiplying by the constant z over y is just going to carry that constant multiple along for the ride. So we'll get 12x times z over y. I'll go ahead and do the other ones just because we're running a little low on time. Del p del y is going to be negative 6x squared z over y squared. And del p del z is going to be just 6x squared over y. So that's some information that's going to be helpful. What else do we need to find before we can just start plugging in numbers and doing the old plug and chug? Huh?
You can find the derivative of x with respect to t, the derivative of y with respect to t, and the derivative of z with respect to t.
Yeah, we could certainly do that. That sounds pretty reasonable. The derivative of x with respect to t, well, if x of t here is 2 cosine of t, derivative of that with respect to t, I think is going to give us a negative 2 sine of t. Derivative of y with respect to t, if y of t is 2 sine of t, that's going to give us a 2 cosine of t. And the derivative of z with respect to t, if z of t is 3t, its derivative is going to be a constant 3. One other thing I think will be useful for us to know, So we can start plugging things into this expression. To del p del x, del p del y, and del p del z is just what is x of pi over 3, what is y of pi over 3, what is z of pi over 3. Because we're going to need to know what those are if we want to start plugging in these expressions. So x of pi over 3 is going to be 2 cosine of pi over 3. Which I believe is going to come out to 2 times a half, which is 1. Y of pi over 3 is going to be 2 sine of pi over 3, which will come out to 2 times square root of 3 over 2, which is square root of 3. I attached the unit circle, by the way, to the back of the sheet if you want to check my work. And z of pi over 3 is going to be 3 times pi over 3, which will just be pi. So if we plug that all in, we'll get x t equals pi over 3 hours. We're going to get del p del x, which is 12 times x of pi over 3 times z of pi over 3, all divided by y of pi over 3, multiplied by our dx dt, which is negative 2 times sine of pi over 3, plus del p del y, so negative 6 x of pi over 3 squared times z of pi over 3 over y of pi over 3, quantity squared, times our dy dt, which is 2 cosine of pi over 3. And finally, we'll add to that del p del z, which is 6 times x of pi over 3 squared divided by y of pi over 3, multiplied by our dz dt, so that's just multiplied by 3. And for the sake of time, instead of plugging, I'll just tell you what this comes out to, because at this point it really just is plug in all of these numbers, do a little bit of trig. It's going to come out to negative 14 pi plus 6 radical 3, which is approximately equal to negative 33.59. And what are our units going to be? We're looking at the derivative of p with respect to t. P is giving us pressure, telling us how many atmospheres of pressure we have at any given point in time. And t is being measured in hours. What should dp dt be measured in? Very hesitant pseudo hands. Tim?
Atmosphere per hour.
Atmospheres per hour, indeed. In other words, the unit for Vp divided by the unit of T. All right, that's going to do it. So the main takeaway from today I want you to remember is the idea of how to differentiate across these diagrams. P with respect to x times x with respect to t, p with respect to y times y with respect to t, etc. You should be comfortable with setting up and doing these diagrams, I think, for solving these sort of problems. I will see you all on Wednesday, where we will start things off with a quiz. Have a good one.